For almost all of human history, we have looked at those stars and asked one timeless, haunting question: do other worlds orbit those stars? Are we alone in this vast, silent cosmos? For thousands of years, that question was left to myths, stories, and speculation. We knew our own solar system well: 8 planets, countless moons, asteroids, comets, all held in the gentle grip of the sun's gravity. But beyond that, we had no proof. No hard evidence, no way to know if planets existed around other stars. Today, everything has changed. We are no longer guessing. We are discovering. We have found thousands of planets beyond our solar system worlds that once existed only in science fiction, now confirmed by telescopes, data, and the relentless curiosity of human beings. These are exoplanets, and they are rewriting the story of our universe. In this deep dive space documentary, we will answer 2 of the biggest questions in modern astronomy. What exactly is an exoplanet? And how many of these alien worlds have humans officially discovered and confirmed as of 2026? We will take you through the full history of exoplanet exploration, break down the ingenious methods we use to find planets trillions of miles away, highlight the NASA missions that made this revolution possible, and explore why these discoveries matter more than you might realize. This is the epic, untold story of humanity's hunt for worlds beyond our own. First, let us start with the basics. What is an exoplanet? The name is simple and direct. The prefix extra means beyond, and solar refers to our own Sunday. So an exoplanet, short for extrasolar planet, is any planet that orbits a star other than our Sunday. That is the core definition, but it covers an astonishing range of worlds. Most exoplanets orbit normal stars, just like our sun: yellow dwarfs, red dwarfs, orange dwarfs, the kinds of stars that make up more than 90% of the stars in the Milky Way. But some exoplanets orbit much stranger stars, massive hot blue giants, aging red giants that have swollen to hundreds of times their original size, and even dead stellar remnants like pulsars and white dwarfs. There are also rare exoplanets, called rogue planets, which do not orbit any star at all. They drift alone through the cold darkness of interstellar space, cast out of their home systems by gravitational chaos, silent and isolated. For a celestial object to be classified as a planet, not a star or a brown dwarf, it must have a mass below the threshold, where deuterium fusion can begin about 13 times the mass of Jupiter. Anything heavier becomes a failed star, not a planet. This clear scientific standard helps astronomers separate true exoplanets from other objects in deep space. For decades, scientists strongly suspected exoplanets existed. The math was undeniable. The Milky Way holds hundreds of billions of stars, and basic probability suggested that many of those stars should host planetary systems. But proving it was one of the greatest challenges in modern astronomy. Exoplanets are tiny compared to their parent stars, and they emit almost no light of their own. They are completely drowned out by the overwhelming glow of the stars they orbit. Finding one was like trying to spot a firefly next to a floodlight from thousands of miles away. For decades, many claims of exoplanet discoveries fell apart under strict scientific scrutiny. It was a frustrating, slow search, full of false hopes and dead ends. Then came the breakthrough that changed everything. In 1992, 2 radio astronomers named Alexander Wolszczan and Dale Frail made history. They detected 2 rocky planets orbiting a pulsar, a rapidly spinning neutron star, the collapsed core of a massive star that had exploded in a supernova. This was the first confirmed detection of exoplanets, and it shocked the entire scientific community. These planets were not orbiting a calm sun-like star. They orbited a dead, ultra-dense, stellar remnant that shoots out intense beams of radiation. The discovery proved that planets could form and survive in some of the most extreme environments in the universe. Just 3 years later, in 1995, astronomers Michel Mayor and Didier Queloz discovered 51 Pegasi b, the first exoplanet found orbiting a main sequence star, a star like our Sun, burning steadily through hydrogen fusion. This giant gas planet, about half the size of Jupiter, orbited its star in just 4 days, far closer than Mercury orbits the Sunday. It was nothing like any planet in our solar system, and it earned the 2 scientists the Nobel Prize in Physics. This discovery launched the modern age of exoplanet science. Before 1992, we had 0 confirmed exoplanets. After 1995, the floodgates began to open. The next question is, how do we find exoplanets when they are so small, dim, and far away? We cannot simply point a telescope at a star and see a planet next to it, at least not easily. Astronomers rely on indirect detection methods, clever techniques that let us sense a planet's presence without seeing it directly. The two most successful and productive methods are the transit method and the radial velocity method. The transit method, used by NASA's Kepler and TESS missions, is elegant in its simplicity. When a planet passes directly between its star and Earth, it blocks a tiny fraction of the star's light. This causes a regular tiny dip in the star's brightness that telescopes can measure with extreme precision. The size of the dip tells us the planet's diameter, and the timing of the dips tells us its orbital period and distance from its star. The radial velocity method, also called the Doppler wobble method, works by measuring the tiny gravitational tug a planet exerts on its star. As a planet orbits, it pulls the star slightly toward and away from Earth. This motion shifts the star's light spectrum, a change that sensitive spectrometers can detect. This method reveals the planet's mass and orbit. Combining both methods gives astronomers a complete picture of an exoplanet, size, mass density, and composition. Other methods include direct imaging, where advanced telescopes block out a star's light to capture the faint glow of a planet, and gravitational microlensing, which uses the gravity of a foreground star to magnify light from a more distant star and its orbiting planet. Each method has strengths and weaknesses, and together they have built the entire catalog of exoplanets we have today. No discussion of exoplanet discovery would be complete without honoring the NASA missions that turned this field from a niche science into a global revolution. The Kepler Space Telescope, launched in 2009, was the true game changer. Kepler stared, fixed at a single patch of sky, for years, monitoring more than 150,000 stars at once. It discovered thousands of exoplanets, more than any other mission in history, including Earth-sized planets in the habitable zones of their stars, regions where liquid water could exist on a planet's surface. Kepler showed us that planets are more common than stars, a revelation that reshaped our understanding of the galaxy. When Kepler's mission ended, NASA launched the Transiting Exoplanet Survey Satellite, or TESS, in 2018. TESS scans nearly the entire sky, focusing on bright, nearby stars, making it far easier to study exoplanets in detail with other telescopes. Today, the James Webb Space Telescope, the most powerful space telescope ever built, follows up on these discoveries, analyzing exoplanet atmospheres for water vapor, carbon dioxide, and other molecules that could signal habitability. These missions are not just tools, they are our eyes on the cosmos, extending human vision across light years to touch other worlds. Now, the question you have all been waiting for: how many exoplanets have humans officially confirmed? As of 2026, the NASA Exoplanet Archive, the official global database for confirmed exoplanets, lists more than 6,100 confirmed exoplanets across thousands of planetary systems. This number is updated every single week as new research is published and new observations are verified. Beyond these confirmed worlds, there are more than 8,000 candidate exoplanets waiting for further data to confirm their existence. That means we have well over 14,000 potential alien worlds already detected, with thousands more waiting to be found. These exoplanets come in every imaginable size and type. There are hot Jupiters, giant gas planets that orbit extremely close to their stars, with surface temperatures hot enough to melt rock and metal. There are super-Earths, rocky planets, larger than Earth, but smaller than Neptune, a type of planet that does not exist in our own solar system. There are many Neptune's icy gas worlds, terrestrial, rocky planets, and even planets that orbit two stars at once, like Tatooine from science fiction. Some systems, like the TRAPPIST-1 system, have 7 Earth-sized planets, 3 of which lie comfortably in the habitable zone. Proxima Centauri b, the closest exoplanet to Earth, orbits our nearest stellar neighbor, just 4.2 light-years away, and sits in its star's habitable zone. Every new exoplanet adds a piece to the puzzle of how planetary systems form and evolve. Why does this matter? Why should we care about planets trillions of miles away? Because exoplanets answer the most profound question we can ask: are we unique? For centuries, humans believed Earth was a rare special world, the only planet capable of supporting life in a lonely universe. Now, we know planets are ordinary. Every star in the Milky Way likely hosts at least one planet, meaning there could be trillions of planets in our galaxy alone. Many of these planets lie in the habitable zone, with the right conditions for liquid water, a stable atmosphere, and perhaps even life. We have not found alien life yet, but every exoplanet we discover brings us one step closer. Exoplanet science also teaches us about our own solar system. By studying worlds vastly different from Earth, we learn how planets form, how they migrate, how atmospheres evolve, and how rare or common Earth-like worlds really are. This knowledge helps us protect our own planet and understand its place in the cosmic story. We are living in the golden age of exoplanet exploration, a time when every night, telescopes around the world and in space are peering into the dark, finding new worlds, and expanding the limits of human knowledge. The future of exoplanet exploration is more exciting than ever. New missions, like the Nancy Grace Roman Space Telescope, will launch in the late 2020s and discover thousands more exoplanets, mapping the populations of worlds across the galaxy. Ground-based, extremely large telescopes will capture direct images of small rocky exoplanets, letting us study their surfaces and atmospheres in unprecedented detail. We are moving beyond just finding exoplanets to characterizing them, learning their climates, geology, and potential to support life. Every discovery reminds us of the infinite wonder of the universe. The hunt for exoplanets is more than a scientific mission. It is a reflection of human curiosity, our drive to explore, and our need to understand where we come from and where we might be going. The 6,100 exoplanets we have found are just the beginning. Billions more wait in the darkness, waiting to be discovered, waiting to reveal their secrets. As long as we keep looking up, keep asking questions, and keep reaching for the stars, we will never stop finding new worlds. Please like, comment, share, and subscribe to the channel.